Good morning. So my name is Aurélie Astoul. So I'm a research postdoctoral fellow working with Adrian Barker, so at the University of Leeds. And today we'll talk about some of my work about nonlinear effects on tidal flows, and especially on inertial waves applied in the convective envelope of low mass stars or giant gaseous planets. So to tell you a bit why it's important for me to study this effect. So far there have been like thousands of exoplanets discovered, and a lot of them orbit really close to their host stars. So for this system, in fact, tidal interaction are really important, and or even shaping like the architecture of the system and also the rotation of the bodies. For example, for WASP-12b, you have the planet that is falling toward its host stars, and this is likely to be due to tidal interactions. So if you want to give a rough estimate of what is the importance of tide in exoplanetary systems, you can calculate this tidal amplitude parameter epsilon. So this is in fact the ratio of the tidal gravity due to perturber body B against the self-gravity of body A. And I have done this on this plot for the planet, so in color. And as expected, this ratio is quite important for close and massive planets. And the larger epsilon is, the greater tidal interaction will be, and also nonlinear effects, especially for small scale features like wave, for example. So to explain you a bit what's happening in body. So considered, again, you have two body. Body B is a punctual and is triggering like tidal flow inside body A. Usually we decompose the tidal response into two parts. So first, what we call the equilibrium tide, which are large scale flows inside the body. So this is mainly this tidal bulge here. And secondly, we have what we call dynamical tides, which are in fact internal waves. And here you have a simulation of inertial waves in a shell. So you can see, as told you, Jiang, that this wave in a shell follow attractors, so periodic straight paths, which takes the form here of shear layers. So with some width depending on the viscosity. And the dissipation of these waves is really the main contribution, in fact, for one of the main contribution for tidal dissipation. So it's really important to have a good estimate of this tidal dissipation. And a few studies have been looking at what is the impact of nonlinearity, thanks to direct nonlinear simulation. So Benjamin Favier did that in 2014. So he performed a nonlinear simulation in a shell. So you have the dissipation here against the Doppler shifted frequency. And you can see in black the linear prediction, which is resonant, highly resonant in terms of the frequency. First important result they found is that, in fact, the self-interaction of inertial wave inside the shell is going to trigger differential rotation, and thus modify the rotation rate, the mean rotation rate inside the body. So if you start a simulation, nonlinear simulation from initial tidal forcing frequency, for example here, because of the wave is going to in fact be Doppler shifted by these new zonal flows. You have in the color bar here the energy inside the differential rotation, and you can explore the range of frequency here. And you can see that you can have order of magnitude of difference between linear and nonlinear prediction for the tidal dissipation. Another thing they find in their simulation is that for some frequencies they have an unexpected angular momentum evolution. They saw that the body is desynchronized, in fact, but for the tide problem, we really expect synchronization of the body, the rotation of the body with the orbital period of the perturber. So that way we took over their work, but in a different approach. We we decompose our flow into the equilibrium tide plus inertial waves. And we also perform 3D nonlinear simulation in a shell using the pseudospectral code magic. And we use a different way to force wave, which is more realistic. We, in fact, the equilibrium tide here is satisfying quasi-hydrostatic balance. And the remaining action of inertial term here, the Coriolis acceleration, is going to act as an effective tidal body force to excite inertial waves. So this is a momentum equation, and we have also the incompressible, the continuity equation for incompressible flow. And so this problem is a bit different from liberation problem. The forcing term is different here. And then we can again perform a nonlinear simulation. So we have again here some dissipation according to the versus the Doppler shifted frequency for 3 different nonlinear simulation here. For tidal amplitude forcing that is moderate, a viscosity and Ekman number of 10 to the minus 5, and a shell aspect ratio, meaning that the size of the shell is as large as the core. And we see again, even if our model is a bit different, we see again that differential rotation is triggered here. So if we start from a forcing frequency, for example, of 1.05, the nonlinear, the dissipation is trying to catch up the linear prediction, so linear prediction in dashed line, but then presumably due to the installation of zonal flow, the tidal dissipation rate is going to be modified from linear prediction. And this modification is stronger when there is clear activation of attractors inside the shell. So I put also here, but not for the same Ekman number, but snapshot of what are the attractors for this different frequency. You can see that for 1.15, you don't have really attractors, shear layers that are excited inside the shell. And that's why the dissipation is not so important. And then the shear flow is not going to be really important. The nice thing in our model is that we don't see any more unexpected angular momentum evolution. In fact, the total angular momentum is conserved in our system. To illustrate how this zonal flow are going to develop inside the shell, I put some movies. So the kinetic energy in the left and the azimuthal velocity in the right. So then I start again. The shear layer is going to be to emerge from the critical latitude, as I told you, Jiang. And then there is some deposition of energy here near the rotation axis. And due to this non-uniform deposit of energy, a zonal flow is going to be triggered inside the shell from the rotation axis to other cylindrical radius. And in fact, the profile, the shape of this attractor, in fact, actually the reflection point here near to the rotation axis and critical attitude here are really determinant for to know what is the final shape of the final flow profile. And I have some example of what I'm saying here. So again, in the middle, you have the frequency 1.1. So the azimuthal velocity, azimuthally average. On top, nonlinear simulation, and on the bottom, linear simulation performed with a spectral code called LSB. And you have the dissipation in linear simulation on bottom. And you can see, for example, for 1.05, the dissipation is more important close to the equatorial plane. And then the zonal flow is going to be stronger at this location in particular and develop from this location. And for 1.15, for example, just note the difference of amplitude of azimuthal velocity and dissipation, meaning that in fact we will have a weaker zonal flow at the end. So a common feature that is shared by all this zonal flow is that they have a symmetry according to the azimuth and also according to the vertical axis. So they are really cylindrical differential rotation profile. Because of that, we can check that an hypothesis. The hypothesis is the zonal flow has something to play with the discrepancy we see between linear and nonlinear tidal dissipation prediction. So what we have done, in fact, is to extract the zonal flow profile at the end of nonlinear simulation. So when the simulation is reaching a steady state, we have done some azimuthal and vertical average of the azimuthal flow. So on the left versus a cylindrical radius. And we have injected this zonal flow in new linear simulation with this background zonal flow profile. And what we find is that the tidal dissipation rate at the end of nonlinear simulation really match with the energy injected by tides in linear simulation with shear zonal flow. And what does it mean? It just means that this is really the installation of zonal flow that is mitigating this tidal dissipation. We have tried to check if this is true for other frequency, meaning that we have done a lot of linear and nonlinear simulation, trying to explore all the other frequencies that are permitted by inertial waves. And we have done that for different tidal amplitude forcing. And first, what we can see is that when we have a moderate or low, 10 to the minus 2 tidal amplitude forcing, so this is the bottom curve, you can see that the difference between linear and nonlinear prediction is not really important, except when we are close to a peak of dissipation, so when the dissipation is strong in linear prediction. And in all cases, we have a good match between the nonlinear dissipation in the pale bullet and the energy injected by tides in new linear simulation with a background shear flow. So this is working quite well. But when we increase the tidal forcing amplitude, we realize that so for some frequency it's working, so the shear flow is going to be stronger. For some frequency we have a good match, so the shear flow is really what is mitigating the tidal dissipation or amplifying the tidal dissipation, but for some frequency it doesn't work. And we have tried to understand why it doesn't work. So we have studied a peculiar case, for example, the 0.002 case and the 0.08 case. So first, for tidal forcing frequency of 0.02, we have looked at what is the kinetic energy in nonlinear simulation versus time here. You can see that it reaches a steady state, but after some times, some oscillations start to grow. And if we do some Fourier transform of the poloidal component of the velocity, here for time range lower than 10,000, meaning before, in fact, the oscillation starts, we have, as expected, the 0.02 frequency, which is a dominant frequency excited in our model. But we have also some superharmonic frequencies, so twice the main frequency and 3 times the main frequency. And we can also multiply by 2 the azimuthal number and give m equal 4 and m equal 6 for 0.6. And if we do it again for the whole time range, so for t lesser than 15,000, we have a lot of frequencies that are excited in our model. So what we can see, what is really interesting here is that if we fix some, for example, if we fix some frequencies 0.13, the m equal 1 mode here, we can recover all other frequencies just by doing linear combination of the frequency and also on the azimuthal number. So what's happening here is that we have some triadic resonance between 0.2 and 0.13 and all other and peaks other frequency also together. So we don't know really why this m equal 1 mode is appearing, but it is sure that it is leading to triadic resonance and to the instability of the flow. Now, so we have also investigated another case which is not working, the 0.8 case, and what we realize is that in fact for tidal amplitude forcing, which is large, of 5×10⁻², we have the presence of co-rotation resonances in our shell. So when the phase velocity of the waves matches with the local zonal flow velocity. And in fact, it corresponds to critical cylinder, as shown here. And on the left, we have some zonal flow for different frequency. And we have indicated also the co-rotation resonances here. So you can see that for a moderate tidal amplitude forcing, the co-rotation is close to the rotation axis and doesn't seem to affect the zonal flow profile. But when the tidal amplitude forcing is larger, the co-rotation resonance seems to affect the zonal flow profile by creating this bump here and making the kinetic energy blow up in some cases. And this is what's happening, in fact, for the 0.8 case. So we have the kinetic energy, the logarithm of the kinetic energy here in new linear simulation with background zonal flows. And you can see that after some time you have a blow up of the kinetic energy. And we have done some snapshot videos again to understand what's happening. Again, you have here the kinetic energy azimutally average. A wave beam is emitting from the critical latitude and is going to be curved by differential rotation. And it must, presumably damped at the co-rotation resonance. But here, what's happening is it seems not really damped, and there is potentially some overall reflection mechanism happening and making the kinetic energy explode near to the critical cylinder here. So that's why the energy is blowing up at the end because of this burst of kinetic energy here. How many time do I have? Perhaps I don't have time for that. So yeah, just to conclude about so we have performed new nonlinear simulation, DNS, of inertial waves using a realistic way to force, to tidally force waves. And in our model, we don't see any more physical evolution of angular momentum, which is good. We still have some differential rotations that are triggered inside the shell, but the nonlinear tidal dissipation rates are closer to the linear prediction as found before. And this can be explained due to the development of shared zonal flow for a lot of frequency, but for some cases, we also seen instabilities appearing, triadic and co-rotation resonance in our model. So there are a lot of the things to do in our model. Investigate the parameter space, lower the Ekman number, and also it could be really nice if we can perform eigenvalue, know what are the eigenvalue, eigenfrequency in our model to know what are the unstable mode actually for the case who are showing instabilities. So yeah, thank you for your attention.
Thank you very much, Aurélie. Are there any questions?
I have a question. I'm Stefan. Stefan Odier. When you have your special case where omega was 0.2, what can you say about the linear response? Is it something you have a kind of resonance for the linear response? Or do you have what is the form of the linear response? Is it related to attractors, or do you have something which is space filling? or global mode?
What I see for the 002 case is that, so in fact, the position of the critical latitude depends on the frequency, and the tiny is the frequency, the closer the frequency, the critical latitude will be to this location here. I'm showing close to the equatorial plane. So in fact, attractors in this case are really like nearly vertical and going, not really going close to the rotation axis.
Yeah, my point was actually you have a peak in the response at a particular frequency. Does it correspond to a particular structure of the linear response, which will not be related to the critical latitude structure, but something else, like a global forcing of eigenmode? Do you understand what I mean?
So
I mean, when we look at your dissipation curve, you really have a peak close to 0.2, which looks like a resonance to something.
But 0.2 is the forcing frequency. So
but in your if you show us your dissipation curve, the previous transparency. You do have
you mean we are close to the dissipation. Yeah.
You have a peak corresponding to a kind of resonance. I suspect that it corresponds to a particular global mode that you forced at this particular frequency.
Possibly. So, in fact,
I mean, there are some papers by.
This is possible.
The response may be related to something which is not related to attractor and critical latitude, but a kind of global mode forcing, which has which fills the volume, and so that which is well adapted for resonance phenomenon in the volume also.
This is possible. So the other case is closer to the resonance here, 1.192. So these two cases have to be explored in more detail. For example, for other case, we don't see a lot of triadic resonance. For example, for the 1.24 case, we are in fact nearly at the peak. We are at the peak of also at a resonance here, and we don't. This is complicated, but I see your point, and I remember the paper you're mentioning. So it's something to explain.
And for this other case, it seems that the co-rotation radius also corresponds to the point where the waves coming from the critical latitude touch the outer boundary. So we expect a strong inflow also created at the radius where the beam touch the boundary. You do observe that, and I'm suspecting that it is also the case here.
So what do you mean exactly? Because for this case, for this 1.824, what I see is it's not an exploding. So nothing is exploding. So this is a green case here, and what I saw in video is like the gravitational resonance is acting like a wall and absorbing all the kinetic energy of the wave being.
But it seems that when it's becomes important is when the beam coming from the critical latitude touch the outer boundary also.
Okay, Stéphane and Aurélie, I propose that we stop.
Thank you. Yes, we can continue in Slack.
If you want to know more about question by Stefan, raised by Stefan. See Stefan's paper published in GFM during, I received the announcement during Aurélie's talk, so this is quite a timely publication. Okay, there is another question by Aurélie by Arthur Lesaut. Maybe you can read it in the chat. First, he's saying that it's very interesting. And how do you expect your results to be affected by the addition of an adjacent radiative zone in the simulations?
So this is a good question. I have not explored that case. So in my model, there is just a convective envelope. I'm not sure how to answer. Yeah, I don't know. But see the work of Christina Ponten, which would answer in the chat.
Thank you, Aurélie. So if there is no other question, maybe we can thank you, Héloïse and Aurélie, for these two talks. And we start in 10 minutes, in 9 minutes.